Hello and welcome. Tonight, we'll be exploring one of the oldest and most fascinating questions humanity has ever asked. Does the universe have an edge? It is a question that seems wonderfully simple at first, almost like something a child might ask while gazing at a sky filled with stars. Yet, the more carefully scientists have searched for an answer, the more surprising the question itself has become. What began as a search for the end of space has slowly transformed into a deeper search for the limits of observation, knowledge, and even imagination. So, find a comfortable place to rest, and let's gently begin our journey into one of the most fascinating questions in science. Perhaps there is something deeply human about searching for an ending. Every path eventually reaches a destination. Every shoreline meets the sea. Every room has walls that quietly define where it begins and where it ends. From the moment we are children, we learn to understand the world by finding its boundaries. We open a book and expect a final page. We climb a hill expecting a summit. We walk through a forest believing that, sooner or later, the trees will give way to an open field. Our minds are remarkably skilled at recognizing edges. And so, when we lift our eyes toward the night sky, it feels almost natural to wonder whether the universe itself must also come to an end somewhere beyond the stars. If you could travel far enough, would you eventually arrive at an enormous invisible wall? Would there be a final galaxy, beyond which there is only darkness? Or would you simply continue forever, crossing an endless ocean of stars without ever reaching a shore? These questions have echoed through human history for thousands of years. Long before telescopes existed, people imagined the sky as a great dome stretching over the Earth. Some believed the stars were tiny lights attached to a celestial sphere. Others imagined vast heavenly oceans or endless kingdoms inhabited by gods. Different cultures painted different pictures, but many shared one quiet assumption: the universe must surely have a boundary. As our understanding of nature slowly grew, those pictures began to change. The invention of the telescope revealed that the stars were not tiny lamps suspended above us, but distant suns scattered across unimaginable distances. Centuries later, astronomers discovered that our own Milky Way was only one galaxy among countless others. The universe became larger with every generation, almost as though it were gently retreating whenever humanity believed it had reached its limits. Yet something curious happened along the way. The more accurately scientists measured the cosmos, the less certain they became that the idea of an edge even made sense. That may sound strange at first. After all, almost everything in daily life has an outside. A house stands inside a neighborhood belongs to a city exists within a country. Even a cloud floats inside the atmosphere above our planet. Our everyday experience quietly teaches us that every object must sit inside something larger. So naturally, we ask another question. If the universe exists, what does it exist inside? It is an innocent question, but one that leads us towards some of the deepest ideas in modern physics. Because the universe is not simply another object sitting somewhere within a larger room. Instead, it may include the very stage upon which every room, every star, every galaxy, and every question exists. That idea is difficult to picture because our imagination has been shaped by everyday life. We have spent our entire lives moving through spaces that already existed before we arrived. We have never experienced space itself as something that could bend, stretch, or possess its own geometry. It is rather like asking a fish to imagine life without water. The fish may understand every current and every ripple, yet still struggle to imagine an entirely different way of existing. Perhaps our minds face a similar challenge when we try to imagine the universe. Sometimes the greatest mysteries are not hidden because they are too far away. They are hidden because our intuition quietly insists on asking the wrong questions. Imagine standing alone on a peaceful beach just after sunset. The sea stretches outward until it gently disappears into the horizon. From where you stand, it almost feels as though the world simply ends in the distance. Yet you know that ships continue sailing far beyond what your eyes can see. Entire continents remain hidden below that soft blue line. The horizon is not a wall, it is simply the limit of your view. Now imagine that the universe might be offering us a horizon of its own. Not a cliff where reality suddenly stops. Not a great cosmic barrier surrounding everything that exists, but a quiet boundary created by something far more subtle, the finite speed of light. That single idea, simple though it may seem, has transformed our understanding of the cosmos more profoundly than almost any other discovery. It suggests that there may be places so distant that their light has not yet had enough time to reach us, even after the unimaginably long history of the universe itself. If that is true, then the greatest boundary in the cosmos may not separate existence from nothingness. It may separate what has had time to tell us its story from what remains, for now, forever silent. And there is something strangely comforting about that thought. It reminds us that the darkness beyond our view is not necessarily empty. It may simply be waiting, patiently, beyond the reach of the oldest light that has ever arrived on Earth. The universe has not promised to reveal all of itself at once. Instead, it offers us small glimpses, carried across immense oceans of space by ancient beams of light that began their journeys long before our planet existed. As we follow those ancient messengers farther into the cosmos, another realization quietly begins to emerge. Perhaps the greatest mystery is not whether the universe has an edge. Perhaps it is whether the edge we are searching for has ever been a place at all. It may instead be something much gentler, a horizon shaped by light, by time, and by the patient unfolding of discovery itself. Not long ago, we stood quietly on an imaginary shoreline, looking toward a horizon that seemed to mark the end of the sea. Yet we knew that the ocean continued long after it disappeared from sight. The universe invites us to make a similar discovery. When astronomers speak about the universe, they often use a phrase that sounds surprisingly modest: the observable universe. Those two words carry an important message. They do not describe everything that exists. They describe everything that light has allowed us to see. At first, that distinction may seem almost insignificant, but in reality, it changes the entire question of whether the universe has an edge. Imagine receiving a handwritten letter from a dear friend who lives on the other side of the world. The letter arrives today, but the words were written weeks ago. As you unfold the paper, you are not reading the present moment. You are reading a small piece of the past that has finally reached you. Light behaves in much the same way. Whenever you look at anything, you are never seeing it exactly as it is now. You are seeing it as it was when the light began its journey toward your eyes. For nearby objects, this delay is so tiny that it hardly matters. The light reflected from a flower in your garden reaches you in an unimaginably small fraction of a second. The moon appears as it was a little more than a second ago. Sunlight, warming your face on a quiet afternoon, left the sun roughly 8 minutes before it arrived at Earth. The farther you look into space, the farther back in time you travel. The nearest stars appear as they were years ago. The beautiful Andromeda galaxy appears as it existed more than 2 million years in the past. Some of the most distant galaxies observed by modern telescopes appear as they were when the universe itself was still astonishingly young. In a sense, every telescope is also a time machine, not because it carries us through time, but because it collects ancient light that has been patiently traveling across the cosmos for millions or even billions of years. That ancient light is all we have. It is the storyteller of the universe. Every image captured by an observatory is another page in an unimaginably old history book, written not with ink, but with photons that have crossed vast oceans of space. This is why astronomers often say that we never observe the universe as it exists today. We observe countless different moments from its past, all arriving together like letters mailed from different centuries. That realization alone makes the universe feel wonderfully different from our everyday experience. Yet it also creates a natural limit. No matter how powerful a telescope becomes, it cannot collect light that has not yet arrived. Suppose there were a magnificent galaxy so unimaginably distant that its light is still making its journey across space. Even if that galaxy has existed for billions of years, we cannot see it until its light finally reaches its hues. It is not hidden by dust. It is not concealed behind a giant wall. Its story simply has not arrived yet. This invisible boundary is what astronomers call the cosmic horizon. Once again, the word horizon is carefully chosen. Just as the horizon at sea does not mark the end of the ocean, the cosmic horizon does not necessarily mark the end of the universe. It marks the limit of the information that has had enough time to reach us. Perhaps the most surprising consequence of this idea is the size of the observable universe itself. You might reasonably expect that if the universe is about 13.8 billion years old, then we should be able to see only 13.8 billion light-years in every direction. That seems perfectly logical, but nature has a quieter surprise waiting for us. While light has been traveling toward us, space itself has not remained still. The universe has continued expanding throughout that entire journey. It is a little like watching a friend walk toward you across a long bridge, while the bridge itself is slowly stretching. By the time your friend reaches the halfway point, the bridge has already become longer than it was when the journey began. The destination keeps changing, even as the traveler continues forward. Something similar has happened to the ancient light filling our universe. As those beams of light crossed the cosmos, the fabric of space gradually expanded beneath them. As a result, the galaxies that emitted that light are now much farther away than they were when their journeys began. Today, the radius of the observable universe is estimated to be roughly 46 billion light-years in every direction, even though the universe itself is about 13.8 billion years old. The numbers may sound surprising at first, but the idea behind them is wonderfully gentle. The universe did not become larger because light traveled faster. The universe became larger because space itself quietly continued to grow while the light was still on its way. There is another beautiful consequence of this picture. From wherever an observer happens to live, the observable universe always appears centered on that observer. If there were another civilization living billions of light-years away, they too would look outward and see a vast cosmic sphere surrounding them. Their observable universe would overlap with ours in many places, yet it would also include regions forever hidden from us. Neither civilization would occupy a privileged center. Both would simply stand inside their own horizon of light. This idea reflects one of the most elegant principles in modern cosmology. The universe does not appear to have chosen a special place from which everything else unfolds. Instead, every observer receives a different window onto the same immense reality. Each window is limited, each window is beautiful, and each window is shaped by nothing more mysterious than the patient travel of light across an expanding universe. Once we understand that our view is only a window rather than the whole landscape, another question begins to emerge almost naturally. If we can observe only a small portion of the cosmos, then what might the rest be like? Could it continue forever without end? Or could the universe, despite having no visible edge, still possess a shape far grander than anything our everyday intuition has ever imagined? Not long ago, we discovered that everything we can observe is only a small window into a much larger reality. The farther our ancient messengers of light can travel, the farther our window extends. Yet beyond that quiet horizon, the universe keeps its secrets. Naturally, another question begins to take shape. If the universe continues beyond everything we can see, does it continue forever? Or does it eventually come back around in a way that simply has no edge? At first, those two possibilities sound completely different. One suggests endless space stretching without limit. The other suggests a universe that is complete, yet somehow without a boundary. Strangely enough, modern cosmology takes both ideas seriously. Perhaps the easiest place to begin is with something much closer to home. Imagine setting out on a long journey across the Earth. You keep walking, day after day, month after month, year after year. You never encounter a giant cliff marking the edge of the planet. You never find a sign announcing that the world has come to an end. Instead, if you continued long enough, you would eventually arrive back where you started. The Earth is finite. It has a measurable size, yet its surface has no edge. You can travel endlessly without ever falling off. For centuries, this simple observation has helped scientists imagine another possibility for the universe itself. Perhaps space behaves in a similar way. Not because the universe is wrapped around a giant sphere floating somewhere else, but because space itself may possess a geometry that does not require an edge at all. This is where our everyday intuition begins to struggle. Whenever we picture something curved, we naturally imagine it bending into another space. A curved road bends across the landscape. A curved sheet of paper bends through the air. A rainbow arches across the sky. Each example quietly assumes there is a larger space surrounding the object. But the universe does not necessarily work that way. According to modern physics, space can possess its own geometry without needing to bend into anything else. That idea may sound almost impossible to picture, and in truth, no human brain evolved to visualize it perfectly. Instead, mathematics describes what our imagination finds difficult. Fortunately, we do not need advanced mathematics to appreciate the basic picture. We only need to let go of one familiar assumption: the assumption that every curve must bend into something larger. Albert Einstein helped transform this way of thinking more than a century ago. His theory of general relativity revealed that gravity is not simply an invisible force pulling objects together across empty space. Instead, matter and energy gently shape the geometry of space-time itself. Imagine placing a heavy stone on a large, soft blanket. The blanket sinks beneath the weight. Now imagine rolling a marble nearby. The marble does not change direction because an invisible hand reaches out to pull it. It simply follows the curved surface beneath it. This familiar image is not perfect, but it captures an important idea. Gravity is deeply connected to geometry. If matter can gently curve space on the scale of stars and galaxies, then perhaps the universe itself also possesses an overall shape. Modern cosmology usually considers three broad possibilities. The first is a universe with positive curvature. In this picture, space is gently curved back toward itself, somewhat like the surface of the Earth, although extended into 3 dimensions instead of only 2. Such a universe would be finite, yet it would have no physical edge. The second possibility is a universe with zero curvature. Here, space is said to be flat. Not flat like a sheet of paper lying on a table, but flat in a geometric sense. Parallel paths remain parallel, and the familiar rules of geometry continue to work even across enormous distances. The third possibility is negative curvature. In this case, space opens outward, rather than curving back toward itself. Instead of closing into a complete hole, it continues spreading in a way that naturally allows for an infinite universe. Which picture is correct? Surprisingly, scientists cannot simply step outside the universe and look at it from afar. Instead, they must become careful detectives. They study ancient light left behind from the early universe. They examine the distribution of galaxies across immense distances. They compare countless observations with detailed mathematical models. One of their greatest sources of information is the faint glow known as the cosmic microwave background. This gentle sea of ancient radiation has been traveling through space for almost the entire history of the universe. Like tiny ripples frozen on the surface of an ancient lake, it preserves subtle clues about the geometry of space itself. Large surveys of galaxies provide another set of clues. By carefully measuring how galaxies are arranged across billions of light-years, astronomers can test whether space bends noticeably on the largest observable scales. So far, these remarkable observations all point toward the same conclusion. The observable universe appears astonishingly close to geometrically flat. That does not necessarily mean the entire universe is perfectly flat. It simply means that, within everything we can currently observe, any overall curvature must be incredibly small. To appreciate how surprising this is, imagine standing in an enormous desert. Wherever you look, the ground appears almost perfectly level. Yet the earth beneath your feet is still round. Its curvature is simply so gentle compared with your immediate surroundings that it becomes almost impossible to notice. Something similar may be true for the universe. Its overall shape could be so vast that the small region we can observe appears almost perfectly flat. There is another fascinating idea that may help explain why. Very early in cosmic history, long before stars or galaxies existed, the universe may have experienced an extraordinary episode of rapid expansion known as cosmic inflation. Rather than thinking of this as an explosion, imagine taking a small wrinkle in a piece of fabric and stretching the fabric again and again until the wrinkle becomes almost impossible to detect. In much the same way, inflation may have stretched the geometry of the young universe so dramatically that any original curvature became extraordinarily smooth. A tiny patch that once possessed noticeable curvature could eventually appear almost perfectly flat, just as a small section of an enormous balloon seems nearly level when viewed up close. Whether the universe ultimately proves to be infinite or merely unimaginably large, one quiet lesson begins to emerge. The absence of an edge does not necessarily mean the absence of structure. Space may possess a shape more subtle than any wall, more graceful than any boundary, and far more difficult to picture than our everyday experience has prepared us for. And once we begin to think of space as something with its own geometry, another mystery quietly steps forward. If space itself has a shape, could space itself also be changing? There is something wonderfully reassuring about the idea of a shape. Once we know whether something is round, flat, or curved, it feels as though we understand it a little better. But the universe has another surprise waiting for us. Even if we could somehow describe the overall shape of space, that shape is not standing perfectly still. It is changing, very slowly, very quietly, and it has been changing for nearly the entire history of the cosmos. When most of us hear the phrase, "the universe is expanding," a particular image immediately comes to mind. We picture a great explosion, fragments racing outward, galaxies flying away from one another through an enormous empty space. It is an understandable picture, but it is not quite what modern cosmology describes. Imagine a loaf of bread resting in an oven. Before it begins to bake, someone presses a handful of raisins evenly throughout the dough. As the bread slowly rises, every raisin appears to move farther away from every other raisin. If you happen to be a tiny observer living on one of those raisins, you might conclude that all the other raisins were drifting away from you. Yet, none of the raisins are actually crawling through the dough. The dough itself is expanding. The increasing distance comes not from the raisins moving on their own, but from the space between them becoming larger. Astronomers often use this gentle image because it captures something important. Galaxies are not simply racing through empty space like debris from an explosion. Instead, the fabric of space itself is gradually stretching. That single idea changes the picture completely. To understand why, imagine placing two small stones on a soft rubber sheet. Now imagine the sheet slowly stretching in every direction. The stones do not need to slide across the surface. Even if they remain perfectly still, the distance separating them gradually increases because the sheet itself has changed. Space behaves in a surprisingly similar way. The galaxies are not being carried outward into some enormous emptiness beyond the universe. Rather, the distances woven into space-time are gradually becoming larger. This naturally leads to another question. If space is expanding, what is it expanding into? It is one of the most common questions in cosmology, and perhaps one of the most difficult for our everyday intuition. Our experience teaches us that every expanding object must have room to grow. A balloon expands into the surrounding air. A ripple spreads across the surface of a pond. Smoke rises into the sky. Everything seems to expand inside something larger. Yet the universe asks us to let go of that familiar habit. Modern physics does not require the universe to expand into another space. Instead, space itself is part of the universe. It is not a stage placed inside a larger stage. It is the stage. An everyday comparison may help. Imagine reading a story printed on an unusual magical map. Over time, the distance between every town on the map slowly increases. The roads become longer, the rivers become wider, the forests drift farther apart. Yet nothing exists outside the map itself. The map does not need a larger piece of paper beneath it. Only the relationships between places are changing. Cosmologists describe this quiet change using an idea known as the scale factor. Although the name sounds technical, the idea is remarkably simple. It is simply a way of describing how the distances throughout the universe change as time passes. You can think of it as an invisible ruler that slowly grows longer. As the ruler changes, the measured distances between galaxies also change, even if those galaxies remain peacefully following the natural flow of space-time. There is another beautiful consequence of this stretching. Light itself is affected. Imagine drawing gentle waves along a long spring. If someone slowly stretches the spring while those waves travel across it, each wave becomes slightly longer. Something similar happens to light crossing the expanding universe. As space stretches, the light traveling through it is gently stretched as well. Its wavelength becomes longer. Its color gradually shifts toward the red end of the visible spectrum. Astronomers call this cosmological redshift. Rather than being merely a curious detail, redshift became one of the great discoveries that revealed our expanding universe. When Edwin Hubble carefully studied distant galaxies, he found something remarkable. The farther away a galaxy appeared, the greater its redshift tended to be. It was as though the entire universe had been quietly growing larger all along. Since then, countless observations have confirmed this extraordinary picture. Yet expansion has not always unfolded in exactly the same way. The universe has lived through different chapters, each guided by different forms of energy. In its earliest moments, radiation dominated the young cosmos. Light and other energetic particles filled nearly everything. As the universe expanded and cooled, matter gradually became the main architect of cosmic evolution. Gravity patiently gathered gas into stars. Stars assembled into galaxies. Galaxies formed immense clusters, connected by delicate filaments, stretching across unimaginable distances. More recently, however, another mysterious influence appears to have become increasingly important. Astronomers call it dark energy. The name sounds dramatic, yet in truth it is simply a label for something we do not yet fully understand. What we do know is that the expansion of the universe is no longer slowing down. Instead, it is gradually accelerating. It is as though the cosmic loaf of bread has begun rising a little faster than gravity alone would have allowed. No one yet knows exactly why. Dark energy remains one of the greatest mysteries in all of modern science. Its true nature is still hidden, and perhaps that uncertainty makes the universe feel even more alive. Not because science has failed, but because discovery is still unfolding. There is one final consequence of this accelerating expansion that carries a quiet kind of sadness. As more and more distant galaxies drift farther away, their light becomes increasingly difficult to receive. Given enough time, many galaxies that are visible today will eventually disappear beyond our cosmic horizon. They will not vanish. They will not cease to exist. Their ancient light will simply no longer be able to complete its journey to future observers. The universe itself may continue growing ever larger, yet the portion that any civilization can observe may slowly become smaller in terms of accessible information. Perhaps the greatest boundaries are not built from stone or darkness. Perhaps they are built from time, from light, and from the silent patience with which the universe reveals its story, one ancient photon at a time. As that thought settles gently into place, another question begins to emerge. If light itself defines the limits of what we can know, then perhaps the true edge of our universe is not a physical destination at all, but a horizon woven entirely from information. Not every boundary can be touched. Some cannot be climbed over. Some cannot be walked around. Some exist only because information has not yet arrived. The universe is filled with boundaries like these. If someone asked you where the horizon is while standing beside the ocean, you could point toward the distant line where the sea appears to meet the sky. Yet the moment you began walking toward it, something curious would happen. The horizon would move with you. It would never allow itself to be reached. No matter how far you traveled, it would quietly remain in the distance, always inviting you onward, never allowing itself to become a destination. The cosmic horizon behaves in much the same way. It is not a wall surrounding the universe. It is not the edge of existence. Instead, it marks the greatest distance from which light has had enough time to reach us since the universe began its long history. Astronomers give this boundary a name. It is called the particle horizon. The name may sound technical, but the idea itself is wonderfully simple. Imagine that every beam of light is carrying a message. Some messages began their journeys billions of years ago and have already arrived. Others are still traveling. Some have not yet had enough time to reach us at all. The particle horizon simply marks the limit between those two groups. Inside the horizon are all the ancient messages that have successfully reached Earth. Beyond it lie messages still crossing the unimaginable distances of space. In other words, the particle horizon is not the boundary of the universe. It is the boundary of the oldest information we have been able to receive. That distinction is one of the quiet revolutions of modern cosmology. For thousands of years, people imagined that seeing farther simply meant discovering more of the universe. Today we understand something more subtle. Sometimes there is more to discover. Sometimes the information simply has not arrived yet. The universe may already contain countless galaxies beyond our view. Their stars may have formed. Their planets may already circle quiet suns. Perhaps, somewhere unimaginably far away, another civilization is looking up at its own night sky. Not because those places do not exist, but because their light has not yet completed its ancient journey. There is another horizon that is even more surprising. Unlike the particle horizon, which concerns light that has already reached us, this one concerns light that never will. It is known as the cosmic event horizon. Imagine watching a small boat drifting slowly away across a calm sea. At first, it remains perfectly visible, then it grows smaller. Eventually, it becomes little more than a tiny silhouette against the evening sky. Now imagine that the sea itself also begins expanding beneath the boat. The farther the boat travels, the faster the water stretches between you. Eventually, even if the boat continues shining a bright lantern every night, the light can no longer overcome the ever-growing distance. Its signals simply never arrive. Something remarkably similar may happen in our universe. Because cosmic expansion is accelerating, There are regions of space from which future light will never be able to reach us. Those places are not hidden by darkness. They are not separated by walls. Time itself quietly prevents their stories from ever arriving. There is yet another idea that sometimes enters this conversation. Astronomers call it the Hubble sphere. Although it is often confused with the other horizons, it describes something different. You can think of it as a region where the expansion of space becomes so significant that extremely distant galaxies appear to recede faster than the speed of light due to the expansion of spacetime itself. That statement can sound alarming at first. Hasn't science taught us that nothing travels faster than light? It certainly has. The important detail is that the galaxies themselves are not racing through space faster than light. Instead, it is the space between us that continues to stretch. The familiar speed limit established by relativity applies to objects moving through space-time. It does not forbid space-time itself from expanding. This is one of those moments when the universe gently reminds us that reality is often stranger than everyday intuition. Fortunately, we do not need to remember every definition to appreciate the larger picture. The particle horizon tells us how far ancient light has already reached. The event horizon tells us which future messages may never arrive. The Hubble sphere helps astronomers describe how cosmic expansion changes the apparent motion of distant galaxies. 3 different ideas, 1 quiet theme. Light does not reveal everything at once. Perhaps the most beautiful consequence of these horizons is that every observer carries one of their own. Imagine 2 people standing on opposite sides of a vast valley on a misty morning. Each sees a slightly different landscape. One notices a distant church hidden behind the trees. The other sees a winding river disappearing into the fog. Neither view is incorrect. Each simply depends on where the observer happens to stand. The observable universe works in much the same way. Every civilization, no matter where it lives, would possess its own horizon of information. No one stands at the center of the entire universe. Each observer simply occupies the center of their own visible window. There is something quietly humbling about that thought. Our cosmic horizon is not a privileged viewpoint. It is simply our place in the story, and that story may gradually become quieter, billions upon billions of years from now. If dark energy continues guiding the expansion of the universe, many of the distant galaxies visible today will slowly disappear beyond the event horizon. Future astronomers may inherit a much lonelier sky. They might never know that the rich tapestry of galaxies we observe today once filled the heavens beyond their reach. Their universe would appear smaller, not because reality had changed, but because the flow of information had become increasingly limited. In that sense, the greatest frontier in cosmology is no longer measured only in distance. It is measured in communication, in ancient light, in the quiet conversation between the universe and every observer fortunate enough to receive its oldest messages. And yet, even these remarkable horizons may not be the strangest feature of the cosmos. For what if space itself possesses hidden pathways, subtle patterns, or gentle folds that cause light to travel in ways we have only begun to imagine? When most of us imagine the universe, we picture an enormous open expanse, stars scattered across darkness, galaxies drifting through unimaginable distances. Everything appears to stretch endlessly in every direction, but appearances, especially on the largest scales imaginable, can sometimes be wonderfully deceptive. Earlier, we explored the possibility that space might possess an overall curvature. Now we arrive at an even more subtle question. Even if we know the geometry of space, could its overall structure still hide a remarkable secret? To understand this idea, it helps to distinguish between 2 words that sound similar but describe different things. The first is geometry. Geometry tells us how space bends. The second is topology. Topology asks how space is connected. An everyday example makes this distinction much easier to imagine. Suppose someone hands you a sheet of paper. You can gently bend it into a curve without tearing it. Its geometry changes. Its overall connections do not. Now imagine rolling that same sheet into a cylinder and joining the two ends together. Suddenly, something entirely different has happened. The paper still exists. Its surface remains smooth. But now, if a tiny ant walks far enough in one direction, it eventually returns to where it started. Nothing magical has happened. The world beneath the ant has simply been connected in a different way. Some cosmologists have wondered whether our own universe might possess a similarly surprising structure. Not because space is literally made from rolled-up paper, of course, but because the relationships between distant regions of space could, in principle, form a complete whole without ever producing a visible edge. If that sounds familiar, it is because we have already encountered a simpler version of this idea. The surface of the Earth has no edge. You can travel east forever without falling off the planet. Eventually, you arrive back where you began. The universe might behave in a similar way, though in 3 dimensions rather than only 2. One possible example is something mathematicians call a 3-dimensional torus. The name may sound intimidating, but the picture behind it is surprisingly gentle. Imagine an old video game. Your little character walks off the right side of the screen. Instead of disappearing forever, the character quietly reappears on the left, walk off the top, and you return from the bottom. The game world feels endless. Yet it actually contains only a finite amount of space. Its edges have simply been connected together. No one believes our universe literally behaves like a video game. The comparison merely offers an intuitive picture of how a finite space could appear endless from within. If the universe possessed a topology something like this, another fascinating possibility emerges. Light itself might someday return. Imagine a single photon leaving a distant galaxy and beginning an unimaginably long journey through space. If space eventually wrapped around itself, and if the expansion of the universe allowed enough time, that photon might complete an enormous circuit and approach us from an entirely different direction. The consequences would be extraordinary. The same galaxy could appear in multiple locations across the sky. Not because there were several copies of it, but because its light had reached us by different cosmic routes. It would resemble standing in a hall lined with perfectly polished mirrors. You see many reflections, yet they all belong to the same original object. This possibility has fascinated astronomers for decades. If the universe is finite and wraps around itself on scales not enormously larger than the observable universe, perhaps the sky already contains subtle clues. Perhaps some distant galaxies have already appeared more than once. Perhaps the oldest light in the universe has quietly traced giant loops through space. Fortunately, there is a way to search for such evidence. The oldest light we can observe is the faint glow known as the cosmic microwave background. It fills every direction of the sky. Rather than searching for repeated galaxies, scientists can instead examine this ancient radiation for repeated patterns. One particularly elegant method looks for what are often called matched circles. Imagine decorating a large balloon with tiny painted dots. If parts of the balloon somehow folded back upon themselves, certain circular patterns might appear more than once. Likewise, if light from the early universe had reached us along multiple paths, astronomers might discover identical circular features hidden within the cosmic microwave background. For many years, researchers have carefully searched for these remarkable signatures. Powerful space observatories, including the Planck mission, have provided extraordinarily detailed maps of this ancient radiation. So far, however, no convincing evidence has emerged. That result is important. It does not prove that the universe cannot possess an unusual topology. Instead, it tells us something more careful. If space does wrap around itself, then the pattern must be much larger than the portion of the universe we can currently observe, or its structure must be more subtle than our present measurements can reveal. This is one of the quiet strengths of science. Ideas are welcomed, imagination is encouraged, but every beautiful possibility must eventually face the patient test of observation. Sometimes nature agrees, sometimes it gently asks us to keep searching. There is another reason this discussion matters. It reminds us that an edge is not the only way a universe can possess limits. A world can be finite without ending abruptly. A journey can return to its beginning without ever crossing a border. A landscape can appear endless simply because its structure quietly carries every traveler back into familiar territory. Perhaps the universe is like that, or perhaps it stretches forever beyond anything we could ever explore. At present, we do not know, and that uncertainty is not a weakness. It is an invitation. Every new telescope, every improved map of the ancient sky, every more precise measurement of distant galaxies slowly narrows the possibilities, allowing the universe to reveal its structure, one careful observation at a time. Yet, even if space itself proves to be beautifully connected, another possibility waits just beyond the horizon of today's evidence. Perhaps our universe is not the only one. Perhaps the boundaries we have been exploring belong to only a single chapter in a much larger cosmic story. For most of our journey, we have remained comfortably inside the universe we know. We have followed ancient beams of light across expanding space. We have explored horizons shaped by time rather than walls. We have imagined a universe that might gently curve back upon itself without ever revealing an edge. Already, that picture feels vast enough to humble the imagination. And yet, some physicists have quietly wondered whether an even larger story may exist. Not because observations demand it, not because evidence has confirmed it, but because certain mathematical ideas seem to point in that direction. This is where we step carefully into one of the most fascinating and one of the most uncertain areas of modern cosmology. The idea known as the multiverse. The word itself sounds almost poetic. Many universes, entire realities existing beyond our own. It has inspired novels, films, and countless works of imagination. But behind the popular image lies something much more careful. Scientists do not begin with the idea of many universes simply because it sounds exciting. Instead, some multiverse proposals emerge naturally while trying to explain something we have already discussed: the remarkable smoothness of our own universe. Earlier, we explored a period called cosmic inflation. According to this idea, the extremely young universe expanded at an astonishing rate during its earliest moments. In an unimaginably brief time, tiny regions of space grew to enormous sizes. That rapid stretching helps explain why the observable universe appears so remarkably uniform, and why its geometry seems almost perfectly flat. For many cosmologists, inflation successfully answers several important questions. But then another question quietly appears. What caused inflation to stop? One possible answer is surprisingly gentle. Perhaps inflation ended only in our region of space. Imagine standing outside on a calm afternoon while rain falls across a wide landscape. At first, every part of the field is covered by the same gentle shower. Then, little by little, the rain begins to stop. Not everywhere at once. Instead, small patches become dry while rain continues falling elsewhere. Eventually, the landscape contains many separate clearings, surrounded by regions where the rain still continues. Some versions of inflation suggest something similar. Instead of rain, imagine inflation continuing across an enormous cosmic landscape. Here and there, inflation comes to an end. Each quiet region becomes a universe like our own. Meanwhile, inflation continues elsewhere, producing still more regions where new universes may eventually form. This picture is often called eternal inflation. The individual universes are sometimes described as bubble universes. Soap bubbles offer a gentle comparison. Imagine blowing bubbles into still evening air. Each bubble forms its own tiny world. Each possesses its own surface, its own interior, its own history. The bubbles may float beside one another without ever merging into a single larger bubble. The comparison is far from perfect. Real bubble universes, if they exist, would not drift through ordinary space. Instead, each would possess its own spacetime. Even so, the image helps us appreciate the basic idea. Our observable universe might be only one bubble among many. If that picture were correct, another fascinating question naturally follows. Could two bubble universes ever meet? Some theoretical models suggest that they might. If neighboring bubbles formed close enough together during the earliest moments of cosmic history, their boundaries could briefly interact. Such an encounter might leave incredibly subtle marks in the oldest light of our own universe. Astronomers have searched for unusual patterns within the cosmic microwave background, looking for signs that such an event may once have occurred. So far, however, no observation has provided convincing evidence. That is an important point. The multiverse remains a scientific hypothesis, not an established discovery. It is an idea supported by certain mathematical models rather than by direct observation. There is another proposal that is sometimes placed under the same broad umbrella, although it arises from an entirely different branch of physics. This is the many worlds interpretation of quantum mechanics. Unlike eternal inflation, it does not suggest distant bubble universes forming in an expanding cosmos. Instead, it offers one possible way of understanding the strange behavior of the quantum world. According to this interpretation, different possible outcomes of certain quantum events may continue as separate branches of reality. Whether this interpretation truly reflects nature remains an open question. Many physicists find it intriguing. Others prefer different explanations. At present, no experiment has confirmed that these branching worlds exist as physical realities. It is important not to confuse these different ideas. Eternal inflation and the many worlds interpretation come from different scientific questions. They are not simply different versions of the same theory, yet they share one quiet feature. Both ask us to imagine that reality may be larger than the single universe we directly experience. If such universes exist, could we ever travel to them? Modern physics offers little encouragement. The boundaries between hypothetical universes are not imagined as giant walls waiting somewhere beyond the stars. Rather, they represent limits of interaction. If two regions of reality can exchange no information, then crossing between them may not be physically meaningful at all. Once again, we encounter the same remarkable pattern. The deepest boundaries in cosmology are rarely made of stone. They are boundaries of communication, boundaries of causality, boundaries beyond which information simply cannot travel. Perhaps that is why the multiverse remains both exciting and frustrating. It expands the imagination while reminding us of the careful discipline of science. A beautiful idea, no matter how elegant, must eventually meet the quiet patience of evidence. Until then, the multiverse belongs neither to fantasy nor to established fact. It occupies a thoughtful middle ground where mathematics suggests possibilities that observation has not yet confirmed. And perhaps that uncertainty is fitting. After all, throughout this journey, the universe has repeatedly shown us that its greatest mysteries are not always hidden behind enormous distances. Sometimes they are hidden behind the limits of what can be observed. Sometimes they wait just beyond the reach of today's instruments. And sometimes they quietly invite us to ask whether the question itself is leading us toward a deeper understanding of reality. Because after exploring edges, horizons, geometry, expansion, topology, and even the possibility of other universes, one final question still remains. Where does the true boundary of the universe end, and where does the boundary of human knowledge begin? Over the course of this quiet journey, we have traveled farther than any spacecraft could ever hope to go. We have crossed billions of years of cosmic history. We have watched ancient light drift across expanding space. We have imagined universes without edges, horizons made from information, and even the possibility that our own universe is only one small part of a much greater reality. And yet, after all of that, the very first question still waits for us. Does the universe have an edge? Perhaps the most surprising answer modern cosmology offers is not simply yes or no. It is something much gentler. Perhaps we are asking the question in the wrong way. Imagine standing at the North Pole. Then someone quietly asks, "What lies farther north?" At first, the question sounds perfectly reasonable. After all, every place seems to have something beyond it. But once you reach the North Pole, the idea of farther north quietly loses its meaning. It is not that the answer is being hidden. It is that the question itself no longer describes anything that exists. Some physicists have suggested that asking, "What is outside the universe?" may eventually belong to the same kind of question, not because curiosity is mistaken, but because the universe may not be the sort of thing that requires an outside at all. Throughout our everyday lives, we become accustomed to nesting one object inside another. A book rests on a table. The table stands inside a room. The room belongs to a house. The house sits upon the earth. Our experience quietly teaches us that every container must itself be contained. But space-time may not follow that familiar pattern. According to modern cosmology, space and time are not merely things that exist within the universe. They are part of the universe itself. If that is true, asking what lies outside space-time may be a little like asking what lies north of the North Pole. The language remains familiar, the meaning quietly slips away. There is an especially beautiful idea that explores this possibility. It is known as the no-boundary proposal. The name sounds mysterious, but the picture behind it is remarkably gentle. Imagine holding a smooth globe in your hands. Your finger can travel across its surface forever, without encountering a sharp beginning or a rough ending. Every point flows naturally into the next. There is no place where the surface suddenly starts. There is no place where it abruptly stops. Some theoretical models suggest that the earliest moments of the universe may possess a similar kind of smoothness. Rather than beginning at an infinitely sharp edge, space-time itself may gradually emerge in a way that removes the need for a traditional boundary. This remains an area of active theoretical research. It is not an established fact, yet it offers a beautiful reminder that nature sometimes solves problems in ways far more elegant than our intuition first expects. Of course, even if one day we discover the true global shape of the universe, many mysteries will remain. What is dark energy? Why do the laws of physics possess exactly the values they do? Why is there something rather than nothing? Could there be forms of reality forever beyond observation? Science has never promised that every question will eventually receive an answer. Instead, science offers something quieter, a way of asking questions carefully enough that each answer leads naturally to another. Perhaps that is why astronomy has always inspired such a particular feeling. When we look into the night sky, we are not simply collecting information. We are participating in a conversation that began long before humanity existed. Every photon reaching our eyes has traveled across immense stretches of space and time. Some left their galaxies before the Earth was born. Others began their journeys before our sun even existed. Each tiny messenger carries a fragment of a story that has been unfolding for nearly the entire age of the cosmos. And every generation receives a few more pages. Our telescopes become larger. Our detectors become more sensitive. Future observatories may reveal gravitational waves from the earliest moments of cosmic history. They may produce sharper maps of the ancient universe. They may uncover subtle clues hidden within the oldest light. They may even force us to abandon some of the ideas we have explored together tonight. That possibility is not something to fear. It is one of the greatest strengths of science. Every discovery remains open to something even deeper. Every answer is held gently rather than tightly. In that sense, the boundary of knowledge is unlike a wall. It resembles the horizon we imagined at the beginning of our journey. Every step forward reveals another distant landscape. The horizon never disappears. It simply moves a little farther away. Perhaps that is exactly how understanding should feel. Not like reaching the end of a road, but like watching dawn slowly spread across a quiet valley, revealing more of the landscape with every passing moment. Tonight, we asked whether the universe has an edge. Along the way, we discovered that the observable universe is not the whole universe, but only the portion whose ancient light has had time to find us. We learned that space itself may be curved without possessing a boundary, and that it continues to expand without needing a larger space beyond it. We found that the deepest horizons are not walls, but limits created by light, time, and information. We explored the possibility that space may fold back upon itself, and that other universes, if they exist at all, remain ideas waiting patiently for evidence. And quietly, almost without noticing, our original question changed. Perhaps the greatest boundary was never waiting somewhere beyond the most distant galaxy. Perhaps it has always been the moving horizon between what the universe has already revealed and what it has not yet had time to tell us. As you rest tonight, perhaps that thought can be comforting. The universe does not become smaller because we cannot see all of it. It becomes richer. Every unanswered question leaves room for tomorrow's discoveries. Every distant horizon reminds us that wonder is not a sign of ignorance, but one of the quiet companions of understanding. So, whether the cosmos stretches forever beyond imagination, gently curves back upon itself, or proves stranger than any theory we have yet conceived, it remains a place that invites us to keep looking upward with patience, humility, and quiet curiosity. And perhaps that is enough. For now, the oldest light continues its endless journey across the silence of space. New stories are already traveling toward us, even if they will not arrive for billions of years. Until then, the universe waits peacefully beneath its blanket of stars, keeping a few gentle mysteries for another night. Good night, and may your dreams wander calmly through the endless beauty of the cosmos.